All right, so let's continue to talk about section 2.5 continuity. So in 2.4, we discussed the one-side limit, and also one very important theorem is limit as x approaches c exists if and only if the one-side limit both exists and the same, right? Equal the same value. So that's the main thing in 2.4. And 2.5, we're talking about continuity. Well, how do we describe continuity or continuous for a given function? Well, for a very easy way to memorize, you think about into this way, guys. If you're starting to draw a graph and then without lifting your pen, during this process, you can see that there is there's no break or stop, right, or jump, right, and and as you can see that this graph it is smooth, right, so when you start to draw, use a pen, it will never lift the pen will never off the board. We call this function it is continuous on this given domain, okay, on this given domain. Now let's look at something that is not continuous. Okay. Again, I in the first part of 2.5, I want you to get to know the idea about the continuity, and then on the second part, we're going to talk about a lot of extensions about continuity. Okay. So starting to look at this graph. Okay. Suppose this is a graph for a function. It passes the vertical line test, so it is a function, okay? And you see that I labeled four numbers, 1, 2, 3, and 4. You see we're starting to draw my graph, And the 2, do you see that it's an empty circle? So that means it's undefined at 2. It's kind of like I need to have a small jump, right? At a 2, and then, so at x equals 2, we call is discontinuous at x equals to 2, okay? And then we're starting to continuous on this part. As you can see, we go. At 3, do you see that from here? And then there's the jump, right? So I have to lift my pen need to off the board and then draw to here. So this at x equals 3, there is also a discontinuity happens. Okay. Now let's continue. So when I move, do you see that? Well, on the left side of 4, my function actually gonna goes to negative infinity. Okay. And after I, cross this negative infinity, and then my function starting from the right hand side of 4 and from negative infinity, and then move to continue. So as also you can see that at x equals 4, there is also a discontinuous. Okay. So this is the brief idea about what is continuous at a point, what is discontinuous at a point. But how do we define that, right? So are there some like math language to support or to help us to check whether a function it is continuous at a given point or not? Well, let's talk about the definition. Okay. So let's look at the definition here. Let C be a real number. We again in our class, at least in Cal 1, all the problems are based on real number system. That is either one interior point or an endpoint of an interval of the domain of a given function. And then here's the conclusion. Function f(x) is claimed to be continuous at C if, here's the key part, limit as x approaches C f of x equals f of C. Okay, so this part is a key thing for the definition of continuous. What we can tell from this condition here? Well, first of all, if you look at the left-hand side of this equation, you can see that the limit as x approaches c, it must exist. What does that mean? That means your left side limit, right side limit must both exist and equal to the same number, that's the capital L. Okay? So from here, let me big arrow. From left hand side, that means as x approaches c from the left, it must exist and equals as x approaches from the right, f of x must equals capital L. Okay. Meanwhile, you look at the right hand side of this equation, f of c also exists and equals capital L. What does that mean? That means at x equals c, function must be defined, and the corresponding value, it must equal that limit. So that's the explanation of how to define the continuous at a point. Okay, so now let's move back to look at this. Okay, we know at x equals to 2, and it's discontinuous. But why is it discontinuous? Do you agree that, guys, f of 2 does not define, right? It's not, or does not define. Okay, right? So one side is not even defined, not even to mention to talk about continuous. Okay. Now let's move on to look at x equals c. Why it is discontinuous? Well, you can see, I don't know, maybe let's put it here. This is 1, this part, someplace this part is 2. As you can see, f of 3 in this problem, it equals 2, right? It exists. However, limit as x approaches c f of x, do you see that it does not exist? Because the left side limit equals, let's say 1, right side limit equals 2. Hence, limit based on 2.4, what did we just learn? Limit as x approaches 3, f of x does not exist. Okay, so, right, we can check that. What about point 4? Well, point 4, we have a lot of things. First of all, fx is not defined at x equals 4. We can already get a conclusion, it is not continuous. Second, the limit as x approaches the 4, as you can see, no matter from the left side or right hand side, it all goes to negative infinity, right? So the limit does not exist. Although we write this situation is, so limit as x approaches 4, f of x equals negative infinity. However, guys, this is just the way we write it out. But limit as x approaches 4 does not exist, okay? It goes to negative infinity, we write into this way, but as you can see, or as you recall from the definition of limit, if a limit exists, then the limit must be a fixed constant. So this is just the way we represent the infinite limit, okay? So I think at this moment, you should be able to have a basic idea about what is continuous. So now let me introduce a couple of names or types of discontinuous. Okay? We already see this. So look at it here. Look at this one here. And you see this graph go and define here, and then move. As you can tell, guys, if I drag this point, okay, I drag this point down to here, in other words, I fill in this part, do you see that my function is going to become continuous, right? So this, we have a name, this is called a removable discontinuity, okay? That means we can fill in this empty dot, and then that will make my function to be continuous, okay? And look at the second one. We go from here, and then there is a jump, right? As you can tell, jump discontinuity, okay? Jump discontinuity. Last situation here, my x starting to go, and then it goes to negative infinity, and then starting from here, it also is from negative infinity and to infinity here. So under this situation, we have a name. This is called the infinite discontinuity. Of course, the two sides of the infinite can be different. This side can go to negative infinity. This side can go to positive infinity. It's still an infinite discontinuity. Or what you can think about it is, you can go. This side goes to negative infinity, but for this side, maybe I don't know, starting from here, as long as one side goes to either positive infinity or negative infinity, we'll all call this is called the infinite discontinuity. Okay, so this is the first part of 2.5, and I'll stop here, and then I will move on to talk about more about the continuity. Okay, so I'll see you soon.